Morning, everybody. Welcome back to Calc 3. Plan for today is I have a quiz for you on Standard 4, and then we're going to be doing Standard 5 for the rest of the class. So just to give you a sneak preview of what's coming for the next in the next week or so. Today we're going to start Standard 5. I'm planning on finishing Standard 5 maybe like part of the way through class on Wednesday. And then we'll jump into Standard 6 towards the end of class Wednesday. On Friday, we'll have the Standard 5 quiz and continue on with looking at Standard 6. And then on Monday we will have our first exam over Standards 1 through 5. And just tell you a little bit about the exam. The way it's going to work is it'll be like 5 quizzes stapled together. Basically, you'll have like 5 pages of questions, page for Standard 1, Standard 2, etc. As a reminder, you can complete as many or as few of those problems as you want/need to in order to get your second mastery or first mastery on each standard. So it's basically an attempt for you to get up to 5 masteries all at once. For the exam, I'll let you have the whole class, even though I don't think it should take that long. You're allowed 1 sheet of notes, front and back, for the exam. Whatever you want written on it, I will not collect it after the exam or anything. Whatever you think would be most helpful for you. Yeah, any questions about the exam? Okay, I've posted some problems from Standard 5. Usual office hours for the next couple days. Today, or this afternoon from 2 to 3. Tomorrow morning at 10. Tomorrow afternoon at 1. Monday morning at 10, or Wednesday morning at 10 before class, and Wednesday afternoon are my next upcoming office hours. Definitely feel free to sign up for retests or for office hour appointments if you'd like to talk about anything related to the class or just, life in general. How can you tell if a clock is hungry? You can tell if a clock is hungry if it goes back 4 seconds. All right, I'm going to go ahead and pass out the quiz for today. This is the Standard 4 quiz. Go ahead and take up to, let's say, about 10 minutes on this one. As usual, I will give you a warning when you're running low on time. And a 4. So it doesn't have to get up. I passed it back. Go ahead and take a few seconds to finish up your thoughts. And pass your quizzes forward, please. Pass your quizzes in, please. Alrighty. So today we're going to be starting Standard 5. Standard 5 is not a very long one. It's going to be focusing on matrices, which we saw way back in Standard 3, where we talked about how you can take the determinant of a 3x3 matrix in order to help us algebraically compute cross products. It's going to turn out that matrices are going to be very important for us going forward for reasons beyond just being able to do cross products. In particular, once we start taking derivatives of multivariable functions, the derivatives we're going to get are actually going to be matrices rather than just single individual values. And so what we're going to be doing in Standard 5 is looking at a bunch of different algebraic operations you can do using matrices some of which will correspond and look similar to things we did using vectors, and some of which will be brand new for looking at matrices. So to start off, I'm going to talk about scalar multiplication. So just like with a vector in Rn, where we can multiply by a scalar value by just multiplying each component of the vector by that scalar, you can do something similar to a matrix to multiply an entire matrix of values by a scalar. And to do that, what will happen is if R is a scalar and A is a matrix, where remember a matrix is just a rectangular array of values. So A11, A12, up to A1n, down to AM1 over to A sub mn. So if we're given a scalar and if we're given a matrix, we can multiply that matrix by that scalar, and what we'll get is just another matrix of the same size as the original one, the same dimensions, where we've just multiplied each component by that scalar. So just like how we can multiply vector by a scalar, same holds true for multiplying a matrix. So as a quick example, if our matrix A, let's say, is 4, 6, negative 3, 0, 1, 9, for instance, and if our scalar R is, let's say, just negative 1/3, we can multiply the matrix by the scalar value negative 1/3, and to do that, we'll just end up multiplying each of the corresponding components, each of the individual numbers by negative 1/3. So if we were to take negative 1/3 of this matrix, 4, 6, negative 3, 0, 1, 9, what is the first row of this of negative 1/3 A going to look like? According to this definition.
Negative 4/3, negative 2.
Yeah. We'll multiply 4 by negative 1/3 to get negative 4/3. And 6 will get multiplied by negative 1/3 to give negative 6/3, which is the same as negative 2. How about the second row? Trying to play you softball so I can ask you much nastier questions later in class.
1 and 0.
Yeah. Negative 3 times negative 1/3 is just going to give us a positive 1, and 0 times 2 pairs is going to give us 0. And then finally, the last row, we take negative 1/3 times 1, we'll get negative 1/3, and negative 1/3 times 9 will give us negative 9/3, which is the same as negative. So multiplying a matrix by a scalar is just as simple as it kind of is for vector scalar multiplication. The thing about a matrix is you oftentimes have to worry about two different dimensions of things you're multiplying by that scalar, width and height. We do one more example really quick. Let's say we have a matrix with just one row to it, because that is totally something you're allowed to do with a matrix, is to just have matrices with a single row or with a single column. If we were to multiply, let's say, the matrix 1, 3, square root of 5 by the scalar value radical 5, we can get another 1 by 3 matrix. Remember, this notation here, m by n, means we have one row and 3 columns. We would get another 1 by 3 matrix from multiplying by the scalar square root of 5. What would be in that 1 by 3 matrix? It'd be root 5, 3 root 5, and I didn't catch one. Yeah, and then square root of 5 times square root of 5, which is square root of 5 squared, or just 5. So in this case, if you start with, say, a 3 by 2 matrix and do a scalar multiple, you're always going to get back a 3 by 2 matrix. You start with a 1 by 3 matrix, like 1, 3, root 5, and do any scalar multiple, you'll still end up with a matrix that's a 1 by 3 matrix. Scalar multiplication doesn't change the size of your matrix at all. Any questions before we move on to addition? So, just like with scalar multiplication, matrix addition is also pretty much the same as it is for vectors. You just add the components across each matrix. So the way this works is if A and B are both m by n matrices, A is A11 up to A1n, down to AM1 over to AMN. So if that and B are both matrices of the same dimension, B11 over to B1n, down to BM1, BMN. So if you have an A matrix and a B matrix that are both n by n matrices, then you can add them to produce a new matrix where the individual components are just the same as they are for the original matrices, just added together. So the top left entry will be the top left entry of A plus the top left entry of B, etc., over to A1n plus B1n, AMN plus BMN, and AM1 plus BM1. Just like with vector addition, you're just adding the same components together from the original two matrices to produce the new one. So for instance, if we had A is, let's say, a 2 by 2 matrix, 1, 4, 0, 2, and B is the matrix 3, negative 5, pi, 0. If we were to add these together, this is a 2 by 2, this is a 2 by 2, we're going to get another 2 by 2 matrix. And what would the first row of this new matrix be? In A plus B. If we were to take 1, 4, 0, 2 and add it to the matrix 3, negative 5, pi, 0.
4, negative 1.
1 plus 3 is 4. 4 minus 5 is negative 1. I agree. How about the bottom row? Oh, I made this too easy. Okay.
5
plus 1 and 2. Yeah, unfortunately, pi and 1 can't really be added together into a single nice thing. So we just have to write their sum as just pi plus 1, or 1 plus pi if you prefer. Can't really simplify that anymore. How about if we had matrix C is 2, 0, 9, 8, and matrix D is 1, 3, 4, 7, 11, 9,999. What can we say about the matrix C plus D in this case? Sure. Different sizes, so you can't add them together. Yeah, C is a 2 by 2 matrix, D is a 3 by 2 matrix. As long as either the row number or the column number or both is different, you can't add the two matrices together. So C plus D does not exist since C and D don't have the same size. So, in other words, just like how in R with vectors, you can't add two vectors that aren't the same dimension to begin with. The same is true for matrices. They have to be the exact, have the same row count and the same column count in order for you to be able to add them. Any questions about matrix addition? So these are the pretty straightforward operations. They're the exact same for matrices as they are for vectors. So not until we get to the next one that things start getting a little bit spicier. So before we move on, just like how we could talk about taking linear combinations of vectors, we could do the same thing and talk about taking linear combinations of matrices. What do you think it means to take a linear combination of two matrices A and B? Any ideas what it could mean to be able to say I have two matrices of the same dimension, say maybe two by two matrices like we have there. What do you think it would mean in order to be able to take a linear combination of those two matrices? Yeah, Sarah?
Combining scalar multiples.
Combining scalar multiple. Yeah, this basically means you take two matrices, A and B, you take scalar multiples of each one and add them together. It means you take something of the form RA plus S times B for some scalars R and S. You know, by the way, looking at this, that R and S are scalars and A and B are matrices, because R and S are lowercase letters, and lowercase letter we're always going to use to refer to a scalar value, whereas A and B are capital letters, and capital letters we're usually going to refer to matrices. And if they were vectors, we'd have something with like a little arrow symbol above them. So as a quick example, just make sure everyone's on the same page. If I were to take 2 times the matrix 1, 0, 3, 5, minus 4 times the matrix 6, 6, 2, 0.1, or decimal one, just to keep you on your toes. This would be a linear combination of the two matrices 1, 0, 3, 5 and 6, 6, 2, 0.1. Because we're multiplying each one by a scalar, and then we're combining them through vector addition. Or vector, or not vector addition, matrix addition. Or if you prefer, matrix subtraction. So if we wanted to simplify this expression, combine everything into a single matrix, what should we do first? Gilbert? So in other words, you're proposing we do our scalar multiplication first, and then the vector addition? I agree. Just like with linear combinations of vectors, you first do your scalar multiplication, and then do your addition. So if we start by doing our scalar multiplication, we'll multiply everything here by 2. You get 2, 0, 6, 10, plus negative 4 times 6 is negative 24. Negative 4 times 6 is still negative 24. Negative 4 times 2 is negative 8. And negative 4 times 0.1 is minus 0.4. And now that we've done our scalar multiplication, we can actually go ahead and add these matrices together. Which when we do that, we'll get 2 minus 24 is negative 22. 0 minus 24 is negative 24. 6 minus 8 is negative 2. And 10 minus 0.4 is... This was 9.6. Indeed. So, linear combinations of matrices work pretty much the same as linear combinations of vectors. You just are going to have multi-dimensional thing. It's not just going to be a single row of values you're multiplying out by scalars and then adding. You've got entire matrices. But it works the same. And now, for something different that we didn't do in looking at matrices, or about vectors, let's talk about taking transposes. So the transpose is just an operation that you can do with a single matrix called taking the transpose of that matrix. Let A equals, that's a typo. If A is equal to the matrix A11, A12 up to A1n, A21, A22 up to A2n, going down to AM1, AM2, over to AMN. So we're starting off with an n by n matrix here. If we want to take the transpose of A, we're going to get a new matrix. In which the transpose of A is going to be the matrix, which will represent by having an A with a little t as a sort of almost exponent, a superscript next to it. And the elements in A transpose are going to be, going from left to right, A11, A21, over to AM1, A12, A22, over to AM2. And the bottom row is going to be A1n, A2n, over to AMN. And here's my question. I'll give you a second to finish writing that down first. But my question is, what did we do, or what change did we make in order to get from the original matrix A to this new matrix A transpose? In other words, how are these two matrices different from each other? Oh. We swapped the columns and the rows. Tim, is that what you were going to say? Yeah, so in other words, if you look at the first row of the matrix A, that's actually A11, A12 up through A1n, that's actually going to be the first column of A transpose. And likewise, the first column of A is going to become the first row in A transpose. So in other words, we can say that the ith row of A is going to be equal to the ith column of A transpose and vice versa. Meaning the ith column of A will be equal to the ith row of A transpose. We've swapped rows out with columns. Another way you could sort of think about taking the transpose, erase these circles. The other way you could sort of think about taking the transpose is to think about taking, like drawing sort of a diagonal down your matrix, so to speak, and then just sort of reflecting the bottom left of the matrix over to the top right and vice versa. You're basically swapping everything to the bottom left of this diagonal with everything up and to the right of it. So A21 and A12 swap. AM1, A1N swap. AM2, A2N swap places, so to speak. So question, if A is an M by N matrix, what can we say about A transpose? What's going to be the dimensions of A transpose? If we're starting off with an M by N matrix, A transpose will be an N by M matrix. M&M's. Getting hungry for lunch. Yeah, that's exactly right. The reason being, if A has M rows and N columns to it, if the rows in A are becoming the columns in A transpose, then that would tell us that since A has N columns, A transpose is going to have N rows. And similarly, if A has M rows, A transpose is going to have M columns, since the rows of A are becoming the columns in A transpose. So let's look at a quick example here. Let's say A is a matrix 2, 3, 1, 0, 4, 8. So A is a 2 by 3 matrix. By the way, when I write out the dimension of a matrix, if this is a quiz or an exam question, like find the transpose of A, you don't necessarily need to write out 2 by 3. I do that to help you in your notes, but unless I specifically ask you, you don't have to write out 2 by 3 each time. So let's say A is this matrix. We want to find A transpose. First of all, what's going to be the dimensions of A transpose? A is a 2 by 3, so what should A transpose be?
3 by 2.
It's going to be a 3 by 2. 3 rows, 2 columns. What's going to be the first row in A transpose? So we go left, right across the top in A transpose. What's our top row going to be? Okay.
2, 0.
2, 0. It's going to be the first column in A becomes the first row in A transpose. So we'll get a 2, 0. How about our second row? 3, 4. And then the last row will be 1, 8. So that the first row in A transpose becomes the first column, or the first row, in A becomes the first column in A transpose, and vice versa. Rows and columns get shifted. Dr. Gerstle, what's the point of taking a transpose? It feels kind of pointless. The reason why we take a transpose is even though a matrix A and its transpose are always going to contain the exact same values, depending on what your matrices are, sometimes it's necessary to take a transpose so that things are the right dimension in order to get stuff done, in order to be able to do algebraic operations. Because, for instance, if we have something like A is, 1, 3, and B is the matrix 2, 4, we can't necessarily add A and B as is. A plus B as is does not exist. But you still might want to be able to think about having some way to say, add these two matrices together. Maybe just want to combine these two values somehow. So you can't add A plus B in this context because A is a 2 by 1, B is a 1 by 2 matrix. But what is something you could add to A instead of just plain old B? B transpose, because B transpose, which just takes the one row and makes it a column, is of the same dimension as A, and then these are two matrices you could add together. So you could add A and B transpose together, or if you wanted A transpose plus B, but A and B themselves you aren't able to add because they're just not the same dimension of matrix. So the reason why we like being able to take transposes, it lets us do algebraic operations involving two matrices that maybe aren't the right dimensions to start with. If you take the transpose of one of them, suddenly things become a little bit cleaner.
It doesn't really matter between you transpose, right? Because they'll
It matters based on the context. I mean, here we could have just as easily taken A transpose plus B, and we'd have ended up with a 1x2 matrix instead of a 2x1. But once we start getting into the calculus side of the class, there will be times where it matters which one you're transposing. Good question, though. For now, yeah, it kind of doesn't matter, but in the future it will. So here's a question. Let's say I have a matrix A. And I take the transpose of A. And then, because I'm feeling a little bit cheeky, let's say I take the transpose a second time. Take the transpose of the transpose. What can we say about A transpose transpose? Is there any way that we could sort of simplify how that's written? Just equal to A? Why is that? And then you should just end up right back with what you started with? Bingo. Yeah, that's absolutely right. If you were to take a matrix and transpose it twice, you're just going to get back what you started with. The reason being, if you start with a row in A is going to become a column in A transpose. But if we take the transpose of A transpose, then what was originally a row and then became a column is going to go back to being a row again. And ditto, a column of A will become a row in A transpose, but will become a column again in the transpose of that. So here, for instance, if we were to take this A transpose and transpose, if A transpose is a 3x2, then the transpose of that should be a 2x3, and the first column in A transpose should become the first row in A transpose transpose. The second column in A transpose should be the second row in A transpose transpose. And so we just end up with the same matrix A that we began with. So transpose cancels itself. A transpose cancels itself out. Sort of like it's sort of like multiplying by the scalar value -1. If you do it once, you get a new matrix. If you do it twice, you get back what you started with. Any questions or comments about transpose? So the other kind of new operation we haven't talked about that you can do with matrices is to multiply two matrices together. And multiplying two matrices is a little bit complicated. More complicated than a dot product of vectors, less complicated than a cross product of vectors. Put it that way. So let's take a look. So we're going to be talking about matrix multiplication. So first of all, we need two matrices. A is going to be an m by n matrix. A11, A1n, Amn, M1. So if A is an m by n matrix, m rows, n columns, and B is going to be an n by k matrix, B11, B1k, Bn1, be nk. If A is an m by n and B is an n by k matrix, we can take the product. A times B is going to be an m by k matrix whose ijth entry is going to be the ith row of the first matrix, A, dotted, so taking a dot product with the jth column in the matrix B. And so whenever you take a product of two matrices, each individual entry in the product matrix is going to be a dot product of some row in your first matrix with some column in your second matrix. Which is a little bit complicated. So let's take a look and see if we can explain what that means, or what that looks like with an example. So let's let A is going to be a 2 by 2 matrix. 1, 2, 3, 4. And B is going to be a 2 by 3 matrix. 0, 4, 6, 2, 1, negative 1. And I would like to multiply these two matrices. 1, 2, 3, 4 by 0, 4, 6, 2, 1, negative. Whenever you're asked to multiply two matrices together, the first thing you need to check is if these two numbers are the same. The column number of the first matrix and the row number of the second matrix. These are going to need to be equal in order for you to be able to take a product. So does the number of columns in A equal the number of rows in B here? Now, what number is that for those two matrices?
2.
A has 2 columns, and B is going to have 2 rows. After we do an example, we'll talk about why do those two numbers need to be equal. But the fact that these are equal tells us we should be able to take the product. And our product, A times B, to find the dimension of the product, you take this number. The number of rows in A is going to be the number of rows in A times B. And the number of columns in B is going to be the number of columns in A times B. So since A has 2 rows, AB is going to have 2 rows. And since B has 3 columns, A times B is going to have 3 columns. So AB is going to be a 2 by 3 matrix, where if we write this out, the top left entry in AB, the 1, 1 entry, in other words, in the matrix AB, is going to be row 1 in A, dotted with the first column in B, so B column 2, or B column 1. The bottom left, here, this is going to be the second row, first column in A times B, is going to be the second row of A, dotted with the first column in B. Row 1, column 2 is going to be A row 1, dotted with B column 2. Row 2, column 2 is going to be A row 2, dotted with B column 2. Row 1, column 3 is going to be A row 1, dotted with B column 3. And finally, row 2, column 3 is going to be the second row of A, dotted with the third column of B. And so when I say A row 1 dotted with B column 1, that just means you go to the first row of A, which is 1, 2, and you write that out as a vector, 1, 2, which if we take the dot product with the first column in B, we're going to get 0, 2. Which, if we then just evaluate, we'd evaluate the same way we could do any other dot product. Which would be 1 times 0 plus 2 times 2 is going to come out to 4. If we take the second row in A, dotted with the first column in B, A has second row 3, 4, which if we dot with the first column in B, it's going to be 0, 2, which when we evaluate will be 3 times 0 plus 4 times 2, going to give us 8. Can anybody tell me what dot product A row 1 dotted with B column 2 is going to be? Anybody just tell me which two vectors am I going to be taking the dot product of here? Are you all going to do the whole thing before telling me leave me hanging? So if we were to take the first row in A dotted with the second column in our B matrix, which what's that going to be the dot product of?
1, 2 dot
1, 2 dot
4, 1.
4, 1. Big deal. First row of A, second column of B, which will be 1 times 4 plus 2 times 1 is 4 plus 2 is 6. How about second row, second column in A times B?
It would be 3, 4 dot 4, 1.
3, 4, second row in A, dot 4, 1. Second column in B, which if we evaluate out, will come out to.
Do you want like the actual number or just 3 times 4 plus 4 times 1?
Yep.
16.
3 times 4 is 12, plus 4 times 1 is 4. 12 plus 4, 16. And then the last two will be 1, 2, dotted with 6, -1. We take A row 1 dotted with B column 3, which will give us 6 minus 2 is 4. And finally, we'll have 3, 4 dotted with 6, -1. Last row in A dotted with last column in B, which will give us 3 times 6 is 18, plus 4 times 1 is -4. 18 minus 4 is going to be 14. And that is how you take the product of two matrices. You just take every possible combination of rows from your first matrix dotted with columns from the second matrix. You have questions about that? So here, our A is a 2 by 2, our B is a 2 by 3. You're able to take A times B, doing a bunch of dot products. What would happen if we took B times A? Would B times A be any different than A times B here? Ellen?
Would it be just the transpose of A times B?
So BA equals AB transpose, like that?
Yeah.
It's a good question. I think we can actually do this. I agree. That was a good guess. I think that BA would be the transpose of AB. If AB and BA are square matrices, meaning they're an n by n, the same number of rows and columns, then you could make some sort of interesting comparisons about AB versus BA. But I think in this case, if B is a 2 by 3 and A is a 2 by 2, the number of columns in the first matrix does not equal the number of rows in the second matrix. And so BA actually does not exist. Since the number of rows number of columns in your first matrix B is not equal to the number of rows in A. So why does this actually cause us issues? I mean, I said as a rule, you have to have the same column number in your first matrix as you do rows in your second matrix. But why is that a rule? What's stopping us from just saying, Dr. Gerstle, I do what I want, and then just multiplying them out using the exact same process? In other words, what would happen if we tried to take some row in the matrix B and take the dot product of a row in B with a column in A? What would go wrong? There? Yeah. If we tried to take a row of the, we were pretty easily able to take a row of A and dot it with a column of B. 1, 2 dotted with 0, 2. That's just dot product of two vectors in R2. Talked a lot about how to do that. But if we tried to take a row in B, say 0, 4, 6, and dot it with a column in A, say 1, 3, we'd get 0 times 1 plus 4 times 3 plus 6 times blah, 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 blah. Can't be done. And so the reason why we have this rule that the number of columns in your first matrix has to match the number of rows in your second matrix is that the number of columns in B, which in this case is 3, is really just going to tell you, if you were to take a row in B, how many entries does each row have. B has 3 columns, so a single row in B is going to have 3 numbers, a 0, a 4, and a 6. Similarly, the number of rows in A is going to tell us how many entries are in each column in A. So A has 2 rows, which means each column of A is going to have 2 entries in it. And so if these numbers are not equal, if this is 3 and this is 2, then if you were to try and multiply B by A, what you would end up with is that you would be taking dot products of vectors in R3 with vectors in R2. And as we talked about way back in Standard 2, that is no way. So that's the reason why these two numbers have to be equal, is because if they're not equal, then you can't actually do the dot products you would need to do when you're taking rows in the first matrix dotted with columns in the second matrix. Anybody have any questions or comments about that? So let's do one more just for practice. Just so I can kind of show you how you don't necessarily need to write this out each time. So in this case, we can't actually take B times A. But what is something that we can multiply by A using something on the board already? Instead of taking the matrix B and multiplying it by A, what's something related to B that we could multiply by A? Matrix related to B somehow that is possible to multiply by A. Take the let's say you can't take the inverse. B is in a square matrix, so we can't take inverses of it. But you're right, we could take the transpose of B, because if B is a 2 by 3, B transpose will be a 3 by 2, and then the number of columns in B transpose will equal the number of rows in A. So we can't do B times A, but we can do B transpose times A. So let's try doing that, just to see what happens. So if we take B transpose, the first column in B transpose will be the first row in B, so 0, 4, 6. The second column in B transpose will be the second row in B, so 2, 1, negative 1. Which, if we multiply by A, is a 2 by 2. 1, 2, 3, 4. This is a 3 by 2. This is a 2 by 2. These are equal, so we should be able to take the product. What's going to be the dimensions of our of B transpose times A? So in other words, B transpose times A is going to be a blank times blank matrix. Huh? It's going to be 3 by 2. It's going to be this number by this number. So we're going to get a 3 by 2. And you don't always necessarily need to write out all of this information every time you're taking a product. If you want to, you can. I tend to just skip this step and just go right to writing out dot products. So I might put something like, all right, first row in B transpose times first column in A, dotted with, excuse me, is going to be 0 times 1 plus 2 times 3, which is going to give me 0 plus 6 is going to have a 6 in the top left corner. This row, second row of B transpose times first column of A is going to be 4 times 1 plus 1 times 3, which is going to be 4 plus 3 is 7. 6 times 1 plus negative 1 times 3 is going to give me 6 minus 3 is 3. And here, you don't necessarily need to write out the dot products each time. If you want to, you can, or if it helps you, you're certainly welcome to. You're also just welcome to just write out what the steps involved that you would do if you took the dot product. 0, 2 dotted with 1, 3 is going to be 0 times 1 plus 2, 0 times 1 plus 2 times 3. This entry here, second row, first column, is going to be 4 times 1 plus 1 times 3, 6 times 1 plus negative 1 times 3, 0 times 2 plus 2 times 4, which will be 8. 4 times 2 dotted with 1 times 4, or plus, excuse me, 4 times 2 plus 1 times 4 is 8 plus 4 is 12. And then finally, if you were to write out the sort of sum slash product corresponding to last row in B transpose dotted with last column in A, what is that going to give us? If we were to try and fill in this bottom right entry here, what last row in B transpose dotted with last column in A.
It's 6 times 2 plus negative 1 times 4.
6 times 2 dotted, or 6 times 2 plus negative 1 times 4, I agree, which when we evaluate will come out to 12 minus 4 is 8. So matrix multiplication ends up being a little bit tough just because you have to keep taking these dot products every single time for every single entry. But, which is probably a sign I'm not going to give you an exam question that's like, here's a 5 by 6 and a 6 by 10 matrix. Have fun doing 50 dot products to multiply those two together. Not going to do it. At least not for a large number of standards. But being able to go through this process is going to be important for being able to do things like when we talk about the chain rule later on, where we have to multiply various derivatives together that's going to correspond to multiply various matrices. And that's going to do it for today. When we come back on Wednesday, we're going to talk a little bit more about determinants. Specifically, how do you take the determinant of a 4 by 4 or a 5 by 5 matrix, and also talk about some shortcut, sneaky methods that you can use to make taking determinants a little bit easier. So hope you all have a good rest of your day. Don't be shy about signing up for retest and office hour appointments, and I will see you all on Wednesday.